Everybody, it is time for Bioeconomy breakfast seminars, and I'm very pleased to see that so many that this topic that we are addressing today has gained such a large interest from you. We actually have about 170 that has signed on. And right now, I think we have about 90 or 100 that are actually listening from all kinds of places around the world. You are very welcome, all of you. And before I let our presenters come in, I just wanted to say a couple of words. First of all, we are letting both of the presenters give their presentations first, and then we'll take questions for both of them at the same time after the last presentation. That's the first thing I wanted to say. I'd also like you to stick around as close to the end, around 10 o'clock as possible, because we are following up with a small Mentimeter questionnaire of about 2 or 3 questions that we'd like you to answer. And then after the seminar, we are recording this. So if you're interested to share this with your colleagues or look at it again, you will receive a mail with the recordings after this presentation. And last but not least, I'd like to say that this is our last breakfast seminar that we will have in 2020. We will have one last one on the 26th of November, and that will be addressing our pilot park that we call Phoenix, that we have here at, thank you very much, Helena. Helena is my co-host. She's not visible, but she's the digital genius of this seminar. So thank you, Helena. On November 26th, we will address Phoenix 2025, if you're interested in that, to see what we can do with our pilot. But back to today's topic. The first person to present is actually my colleague Peter Rättö, who's a scientific advisor at RISE. He's also actually an associate professor at KTH and an adjunct professor at Karlstads University. And I'm very happy to be able to let you in, Peter, to give your presentation on research to replace fossil-based laminates.
Okay, thank you, Pia. I'm just gonna share my screen here. My presentation. I will be addressing research to replace fossil-based laminates, and I will be concentrated quite a lot on what's been done at RISE, of course, but also a little bit from KTH and some from Karlstad University. I will also concentrate quite a lot from wood-based resources and what we can actually do in the pulp mill. Let's see. So if we're, I'm gonna have a laser pointer. If we start with looking at bioplastics, just to give some definition about it, there are various definitions regarding bioplastics, and you can also, they're not really that precise. I looked at the European bioplastics, and this is what they came up, and I've seen this one in other places too. Bioplastics are bio-based, biodegradable, or both. So you can say that you have 4 groups here. You have the conventional plastics, which are conventional fossil-based plastics like polypropylene, PET. And then you have plastics that are from bio-based resources but are not biodegradable. Like if you make polyethylene from bio-based resources, that's possible today. Then we have the part also where you have fossil-based plastics, but are biodegradable. That could be PBAT, PCL. Polyvinyl alcohol is actually biodegradable in solution. You can also have make PBS from fossil-based resources. And then we have the bioplastics that we would say that they're both bio-based and they're also biodegradable, like PLA, PHA, PBS, as long as they're made from bio-based resources. So that is a little bit on definitions, and what I'm going to be talking about is quite a lot has to do with what we're talking about, conventional plastics that we use as packaging barriers, and how we're using wood polymers or research about wood polymers to replace these. If we look at the barrier challenge as such, we usually have a quite good oxygen barrier, or you have a quite good water vapor barrier. Usually there are a few exceptions where you actually have both that are good. Polyethylene, as an example, is an excellent water barrier, but it's a poor oxygen barrier. Cellulose is actually a good oxygen barrier, but it's quite water sensitive, and it's not really that good of a water barrier. It's the same thing with EVOH. There are, to say, two exceptions. One is PVDC, which actually shows up quite good oxygen and water vapor transmission rate, and you have the liquid crystalline polymers, which also do. I think that both of these are actually that you have a high crystalline content here, especially the LCP. Most of these materials are applied with extrusion coating. I should also say that. If we look a little bit on what we're trying to use to replace fossil-based plastics. Oh yeah, I also forgot. Normally you would make a multi-laminate consisting of two or a couple of these plastics like EVOH and polyethylene to get a good water and oxygen barrier. If we look on what resources we're going to use, what we're looking at RISE, for one thing, to replace these kind of plastics, we have the pulp mill, such. You can actually produce nanocellulose from there. That is a process that other people know quite a lot more about than myself. Generally, just try to separate the fibrils and get the material from there. Then we also have side streams like hemicellulose and lignin. There's also quite a lot of extractives, especially within bark and so. These are usually sent to the boiler for energy production in the pulp mill. So you have quite a lot of pulp mills that are actually energy producers because of this. One idea is to use what you're actually burning to make materials. Also, that's one of the basic ideas here. Nanocellulose, if we go through them one by one, this gives an excellent oxygen and grease barrier. It's quite hydrophilic. It's very water sensitive too. The advantage there is actually that you can disperse it in water, which means that you can put it, have a water carried system. It's biodegradable. The problem is that you have a very high water interaction between the cellulose and the water, and that gives a high viscosity, and you somehow have quite low solids contents here. On the other hand, you have quite good film formation properties, where you actually have quite nice films forming from it. One way to get around the water sensitive, the simplest way is just to put another barrier as we do. Here is what we would say Friday afternoon experiment that we did a couple of years ago, where we actually took a water barrier and printed onto an NFC film. You can see the ones on the top. This is the unprinted, the printed, and we also put some pigment into the barrier just to see the coverage. And it's a very thin film here. We printed twice on each side. The difference when you look at the water drop is quite high, quite large. You have the water spreading out on the NFC film, whereas when you have the barrier, you actually have a hydrophobic surface, a little bit water repellent. What's actually the interesting part is that once you let time go, that this drop would actually dissolve into the material while this one would evaporate. The advantage here was that we actually got a material that could be useful for packaging, just by simple means here, I would say. We haven't had a chance to follow this one up, but I think that probably in the near future, I hope that we can do something like it. Another way around it is to look at composites. This is actually work, get this slide from Rosanna Moriana from her time at KTH, when she did research there. Where I looked at bark and oat husks to have pectins, proteins, and mix it with CNC. And the advantage that they could show there was that they would actually have bare barrier properties. Nanocellulose is a little bit porous as such, and these kind of materials would fill out these pores. It would actually improve the oxygen barrier, even if it's something that's not a good oxygen barrier. And they would have a better water resistance here too. So here they could make a nanocomposites that would work a lot better. If we go on with hemicellulose, this is also a wood-based polymer that would kind of function as a glue in the fibers. This can be extracted from residual material streams. It's done at various sites. Actually, it's hydrophilic, it's water sensitive, can be dispersed in water, and it's biodegradable. It's quite similar in properties as nanocellulose in many ways, but it might be a little bit easier to handle in the coating. And actually, there are barrier coatings today that are based on hemicellulose, I should say too. The problem with both hemicellulose and nanocellulose is that when you get to higher relative humidity, you have barrier properties that deteriorate. We did this, I think it's 2 years ago that we published this one at PaperCon, where we actually had a project that was running 3 years. We had worked quite a lot with nanocellulose, with characterization of nanocellulose, chose one, and we did pre-hydrolysis trials just to see that we could actually produce a little bit more. We used ultrafiltration there and resulted with about 5 kilograms of dry content hemicellulose. At the dry content of 10%, raising that dry content takes a lot of work. So we had, when you're doing things in lab, these things producing 5 kilograms is quite a lot. For one thing, I should say. So the step here is quite large. We actually had a coating manufacturer who helped us to build up a coating formulation, then also actually manufactured about 50 liters of coating color with this. This contained fillers and plasticizers and other things too, of course. But we ended up with that and went up to get some paperboard and made some coating trials in the pilot coater at relevant industrial conditions. These are actually pictures from these trials. And this is the result with the roll here. And the brownish part here is the hemicellulose coated board. It's brown because you have a little bit of lignin within the hemicellulose coating too here. We were able to coat this in pilot scale, and we had a decent grease barrier. So what we could show here was that we could do this. It was possible to do it in this way. Problems with hemicellulose when you look at it is also that it's actually quite brittle, and that makes it sensitive to fast drying for once. But I think that part, coating manufacturers and people running the coaters have a quite good idea of how they should proceed with that. The problem we also saw that we had cracks, that you get cracks during converting operations, and these are actually some images of surface of hemicellulose that I had a master's thesis student, Andreas Riedel at Karlstad University, who actually did the work on this, and you can see the cracks here around the creasing line here. You actually have the creasing line there, and you have the cracks here just beside it, and this is just a magnification of the whole thing. And the problem with these kind of cracks is that you don't see them with pure eye or in light microscope. You need to go to quite high resolution in order to see them, but they are quite harmful when it comes to oxygen barrier properties. Here is another example on how you can proceed to get this to have a better water resistance of hemicellulose, and this was actually also done at KTH that I received from Rosanna Moriana from her time there, when they mixed CNC with Xylan in different amounts, and they would actually improve the barrier properties when they use these kind of mixtures or non-composites that were. So I think this is definitely a possible way forward in order to improve barrier properties, or maybe even the rheology of hemicellulose and non-cellulose. Then we have the third one, which is lignin. This is, we actually have a process or with the selling process called lignin boost, where you can actually extract lignin in quite large amounts. We have a pilot facility in Bäckhammar where they actually can do this. So the amount, we have quite a lot of lignin available in that way. Lignin is a good material in some ways. It's water repellent, such hydrophobic. You can actually use it. It's also UV absorbing. It has antibacterial properties, and well, you could make it biodegradable too. This is actually some fibers that have been treated with lignin on the surface, and you can see the water drop here, that it's not dissolving at all, but it stays on the surface. So I mean, there's definitely a potential here. We actually did tries with pre-tries with it. This was also some years ago that we did tries with the acetone, solved it in acetone, and impregnated liner with it, and we could actually improve both the stiffness and strength, especially at high relative humidities. We also had a very hydrophobic paper, so if we could make this work with water, it would be really nice to as a replacement for starch. I know that there have been other research done in a similar way with solvents and making lignin barriers. The problem is that you can't really use these kind of solvents in an industrial environment. We have been working at Karlstad University too with lignin. This is an example from Asid Javid's doctoral thesis, where he mixed starch lignin and cross-linked it. the improvement here, or the thing here, when you mix it with lignin and starch, is that you actually have solubilities at lower pH. Lignin is soluble at higher pH, at pH 14, but the problem is that you when you have done that, it's not really water repellent anymore. Here we could keep some of the properties by lowering the pH and cross-linked it with the AZC. We had something that resembles of a water barrier, 100 grams per square meter, 24 hours. It's not a good water barrier, but it's at least stopping some water here. So kind of as a first trial, you can see it as okay. What happened when we actually looked at starch and lignin and took the cross-link, we actually increased the stiffness of the materials, as you can see the DMA measurements here, 0, 6, and 11 parts of AZC. What we also could see was that we also had a better chemical stability of the material itself when we looked at how much of lignin or starch, how much starch that would actually be dissolved in diionized water, alkaline buffer, or food simulant. You could actually see that if you mix with lignin, you have less starch going out, and if you cross-link it, it's even more stable in that way, and that's especially significant for the food simulant here. We could also see that we had less lignin being extracted from the material when we put it in alkali or in acid too. So we could draw the conclusion that we had better stability here. We did some pilot tries later on. I don't know if they're published yet, but I think they are actually there. So the system could be applied there. Anyway, if we look at challenges for it, is really to apply this in a regular color, you need to find some way of making it soluble in water. And we're working quite a lot on that one, both only at RISE, but also with partners. We're also, there's also a problem with the brittleness. Trying to make a film with lignin is quite hard. And converting is a nightmare in that case. So finding good plasticizer is one thing, and then there's this order thing. I have a former colleague who says it's not a problem to remove the order, so I just have to take his word for that one at the moment. Once we have solved these challenges, we actually have with the possibility of scaling up. And scaling up, I think that's something that we need to do here. And scaling up the results of KTH would be definitely very interesting to try to do. The brittleness of these materials, of course, moisture sensitivity of Nanocellulose and Hemicellulose, but there are some ways around it, the order of lignin, as I mentioned. Once we have tackled these, we actually have barriers that can be produced from material streams in the pulp mill, and that can be applied on the board machine. And hopefully we have a packaging material that can be reslushed and reused in paper and board without any other treatment. By then, I thank you for your attention.
Thank you so much, Peter. You actually have a bundle of questions. Well, start my video, that's what I wanted to do. Thank you very much. We will sum up all the questions after Mikael has made his presentation as well. I forgot to say that I will be your moderator today, if you haven't noticed. And my name is Pia Wagberg, and I work for RISE. And my co-host for this event is actually Helena Halonen, who is doing all this digital stuff in a very, very good way. So anyway, without further ado, Mikael, we will introduce you as the Business Development Manager at Biomaterials Stora Enso. I'm very interested in hearing what you will have to present. Our whole idea with this breakfast seminar is to have one presentation from RISE and one presentation from one of our collaborators in different ways, and you are very much so. So with your PhD in polymer science, I think you have a quite deep understanding of the research, but we will listen to your presentation now from Stora Enso, okay?
Thank you very much, and thank you for inviting me to this. Yes, I've been working in 20 years now, actually, with attempting to replace plastics with bio-based materials, or preferably renewable or biodegradable materials. What exactly is the best choice here? That depends on the market. Some want the materials to be renewable, some others want them to be biodegradable. Some others want them to be recyclable, etc. And some others don't want anything of that. So it's a diversified market and looks different depending on where you are in the world. What I will present today are some examples of products that Stora Enso already have. Stora Enso has a quite broad portfolio of many products. I just exemplify some snapshots, which are options to plastics, I would say. You have different approaches here if you want to get rid of plastics. One is to make a material that mimic plastics to its properties. So you get something that is very similar to plastics, the traditional plastics, but it's either biodegradable or renewable. Or you can also look at the customer needs. What service do they need? And how can we provide that without using plastics? And I would say that Stora Enso has a combination of that. So there are different products with different approaches. So I'll give you some examples here. First of all, I would just like to say a little bit about Stora Enso. We're around 26,000 people working here. We're divided into different divisions. We have many different products for different purposes. What unifies us are a vision of that everything that is coming from the oil source today can come from the forestry today or tomorrow. So our driving force is to replace them within these different fields. Obviously, when we have this driving force, we spend a lot of time and money on R&D. And we also have a long-term target here that we should have always 15% new products to replace the old ones on the market. And of course, the target here is among others, is to replace plastics. So let's get into it. Here's one example that we released not too long time ago, actually. It seems like a small step for Stora Enso, but a big step for the humanity. It's basically to replacing plastic glass ice cream tray. In this case, can of course be used for others. And this is from one of our boards, Capforma Natura board. So this is we targeted one product here for one brand owners, but this is spreading, of course. And I think this is the right way to do it. It's good to have long-term vision, but at some point we need to dig it down to something that we can put on the market in a quite reasonable time. So this is a product that we have out at the moment, and we save some tonnage of plast on this. Let's go on. Here's another option, which is for another ice cream producer. This is also something that seems to be, it's basically a paperboard that we have. It's with renewable polyethylene. For researchers who are, of course, far in the future, this may not sound so fantastic, but when you're going out there, you're going to face a lot of problems you never thought about on the researcher's desk. So in that sense, it's very good to take this step. I would say this is something that actually works. And the engineers spend a lot of time and efforts to actually make this running. So this I'm very proud of to show you. But let's go further. We have many more options. This is something else that we came out with a while ago, which is an attempt to replace plastic tubes. And this is a huge packaging type in the world. Just go to this packaging exhibition, you're going to see a lot of tubes of different kinds, mainly for cosmetics, but also for other type of products. So imagine that we should replace the plastic tubes with this one. Then we would reduce the plastic consumption by 70%. And this is something that's out, a product we have. We developed together with this ice automation. And we're now working on also a bio-based lid and spout for this tube. So the target market here are cosmetics or other type of products that's packed in tubes today. And this is a very big thing, actually. This is renewable straws. I was once working with the SRG Combi block, and I know that market is quite tricky. We want to be renewable, we want to be environmental friendly. Still, we have these straws that is littering everywhere. It's so light, etc. So this is an option. This is a new option. There are paper straws out on the market as well, normally based on technologies that are quite old, because the paper straw, they were there before the plastic straw came around. This is a new option. So this is something that we offer together with a company called Stora. And anyone can order them actually on biofutura.com. So you don't have to be a big customer so to buy these. So let's go further here. This is another thing that we developed together with a company called Artaplast. It's on the market. Probably you've seen it on the shelves here in Sweden at least, and some other Nordic countries. This is a way to replace the regular plastic trays for dairy products, crème fraîche and other products, which reduces the amount of plastics tremendously. So this is quite interesting, and it seems to work very well also out there. Another example we have are these one, which I think is quite cool. This is developed together with a German company. And this is, you've probably seen this for juice and for also Löfberg's different coffee products out there and tea products. So I think it's quite amazing. So this is a paper-based packaging with, still it's an aluminum coating on, but I'm still happy that we can replace quite a lot of this aluminum compared to regular aluminum cans and so on. And of course, with a very good shelf life on the food packaging that we pack into this. So it's named Carter Can. This is something else that you might have seen on the market. It's a paperboard, Natural Life. It's for milk and so on for our customers. It's renewable, I would say. It's with a green polyethylene instead of the regular one. We have removed the mineral coating as well onto this to make it even more recyclable. And actually, this type of board was very common when I was a little. Not exactly this one. This is a bit better, but this raw brown board. And of course, for the customer, I mean, you want the product, right? That's the important thing. And it's also signalizes, of course, environmental friendliness. You don't need to have this perfect, shiny, white packaging all the time. So this is a very nice product, I would say. This is something we call pure fiber. It's a molded fiber, like the one examples you can see here. This seems to grow now in the world more and more. So it's, I think the base technology is not new. It has been around for a long time. You press the paper and then you mold them to these different type of products. We know also that there are some companies out there that have developed quite nice recipes. They could be fantastic, almost like plastics, basically. As more additives you have into this, as more fantastic surfaces you can get, but also as long longer time it's going to take to dry them, and it's more energy that will be consumed to do it. So I would say what they have succeeded with here at Stora Enso is a quite good balance between this very nice performance and also very nice energy profile of what they produce. So this basically lowers the carbon dioxide footprint with 75% compared to other products. So it's renewable and recyclable, and can be used to a lot of different type of contents, as you can see here, and usages. Tray form is an option we have also for replacing the plastic trays and aluminum trays for many markets. There are options that's also for ovens. Some of them are then biodegradable, I would say. It's biodegradable coating on them. Yeah. Something else, a box for fishes. You can put ice into it and fishes and whatever you need. You can even put water into it. This is an option to these regular white polystyrene boxes that you've seen for so many years. One of the problems I would say with these styrene boxes is that when you break one, you have these small expanded balls that spreads everywhere, which is really not nice. That won't happen with this one. So it's recyclable. It's paper-based. It's a very thin layer of PET coating on the insides. It's fully recyclable, of course, including the inner layer of the PET. So this is a very good option to this expanded polystyrene boxes, these frigolite boxes or whatever they're called. This is another nice innovation. Actually, we got the ScanStar Award 2020 for this one. Instead of buying your pallets, if you have a small pan at home, and instead of buying them in plastic bags, so you can actually buy them in this box. It's quite nice. It has a quite nice opening function, so it makes it easy to pour the pellets. And of course, also when you empty the package from these pellets, you can burn the packaging as well. So very neat. It's something else that it doesn't solve the world problem, of course, but it's quite nice anyway. We get also a ScanStar Award for this one, replacing actually the flower pots that you can buy in the store. It's normally made of plastic, PS or PP or so. Here you have something to replace it, and it's very easy to carry home. I would say it's a very practical type of gift packaging. And I was foremostly impressed by its simpleness. It doesn't have to be so complex. So if you can replace plastic by simple means, I think that's a better way to go. This is something else that we have. It's intended for the e-markets, which is of course increasing rapidly, not least thanks to this corona pandemic we have at the moment. And this is a great selection of products actually, and they're coming up more and more to this. So, and this is a very good option also, replacing plastics. But I think for the customers, it's also, actually fulfill the purpose here in a safe way, transport the goods. And you have a very nice also sort of unboxing experience of this. So it's a very complex-free type of packaging. Really nice indeed. You can check the homepage also. You can find more there. It's quite nice. This is something else that I would like to show you. This is what we call Durasense. We've had it on the market for a couple of years, 2 years now, maybe something like that. So it's fiber-based composites. So it's made of wood fiber mixed with plastics. Intention here is to replace a big part of the plastics. It could be made fully renewable. We have such an option also. The overall aim here is to have a durable product we can use for many different type of products, also for those who should last a long time. So it's not just for a quick use packaging, this is also for long-term products to reduce the plastic usage, which we think is very good. And yeah, it can be also, we have this Durasense Eco here, which is fully renewable. Quite nice. yeah, foremostly Stora Enso is a material company. Another type of material we have is also lignin, and we do a lot of work on that to see how we can utilize it in a good way. Today we sell lignin. Could be used for a lot of different type of applications. We have our own development on this, but I'm sure also we have customers who are developing lignin products. And here I can see potential to replacing plastics, glues, coatings, lots of different kind of things in different industries. This is something we're about to develop also, which is quite nice. It's also a replacement of the regular foams that you have today, polyurethane or so. It's made of cellulose. You can use it for insulation, but also damping, shock absorbing into packaging, etc. Liquid absorbing and so on. So this is quite nice thing we do together with a company called Cellotech, which actually is a part of Stora Enso Biomaterials at the moment. So it's a quite impressive product they have developed, I would say. Yeah, there's something else we have also, which is microfibrillated cellulose, which is another cellulose product. And we have them formed as a strength enhancer at the moment in our new Natura board for lighter board, I would say, with maintained mechanical properties. This is a way of source reduction in its best way, I would say. Of course, the MFC can be used for a lot of different kind of things. For instance, we can also, make it to a barrier or something else. Yeah, my time is running out. I will just give you some short examples of whatever we can do out of the boards we have. So this is something we call Trayformer Bio, which is a board with a bio barrier coating on. Perfect for a lot of different type of applications. It's sort of biodegradable. This is a Tambrite PE green, which is a barrier board coated with renewable polyethylene. And this is a double coating with it's called Capforma Special PE green. So it's also a board with renewable polyethylene. This is again another option for a pigment coated board with a biopolymer barrier as well. And this is a double coating then with renewable polyethylene for different type of products. And out of these boards, the customer can make whatever product they want, and we're helping them with that, of course. So that's all for me for now.
Thank you very much, Mikael. That was a very good a very good presentation of what's actually out there on the market. Interesting. We have quite a few questions, and I'd like to invite Peter as well to show your face. This is exactly what we wanted to have this kind of a combination of both what's happening on the research in this area and what's out there on the market. So let's go to the chat room. I will take up we had quite a few questions, and they're kind of overlapping a little bit, but I will start from the top and see. We had Salatalo had the first question here, and this is, I think, directed towards Peter. How long functional time has nanofibrillated cellulose and hemicellulose barriers as grease barriers under normal conditions, meaning room temperature and RH? Are we talking about weeks or months? Peter, can you answer that?
Well, I wish I could. We haven't really tested it in that way. When I said that we had a decent grease barrier, it's rather that we look at half an hour or something like it instead. But of course, this needs to be tested. Then it also comes to the other answer that should, as a scientist, I would say it depends on what type of oil you have, molecular weight, and so on.
So what you're saying is it's like all like it is with research, that there are many options and you have to look at.
Yeah, but I mean the short answer is that we haven't tested it yet in that way. We test if something has the potential to work or not in research.
Okay, so Peter, you have another question here from Juha Lipponen. What if you use MCC crystals instead of CNC?
Yeah, why not? I mean, that might actually be appropriate too. And in this particular example, they use CNC. So, but that's definitely something that can be tested too.
Okay, great. Let's go to the next question from, I think this is a colleague of mine, Mikael Magnusson, referring to the matrix of bio-based biodegradable barrier materials. There are good barrier properties on those that are both at the top right cell in the matrix, referring to your matrix probably, Peter. What would you say is the major challenge for the bio-based and biodegradable barriers? Why are we not already using them? And in adherence is the issue of combining moisture, oxygen, moisture/oxygens or other.
Well, I mean, combining moisture and oxygen is that is an issue even with fossil-based plastics, most of them. I would say that we have, depending on whether you're looking at the dispersion coating or an extrusion coating, the first one being something that you disperse in water, the second one is that you actually apply a melt. Depends a little bit. If we stick to dispersion coating, is that it's not really that simple to put a barrier onto porous paperboard and have it cover the whole thing, and that is something that we're working on quite a lot at Karlstad University to look at. I hope we also will address it in the next research program at Rice. Then there is, if we're looking at the extrusion coating, we're talking about thermal stability, that you have a very narrow process window sometimes. And then there's also this brittleness, mechanical properties during converting, and of course price. But I think also that Mikael has actually showed some examples where these materials are used, so they are actually used in some cases.
Yeah, and that actually brings me to the next question from Anna Altner, who before she listened to Mikael said that research results, how close to commercialization, what is the challenge and the timeline? And I think maybe we should address that question to Mikael, because there is actually some commercial examples that you've shown. But what do you think about this question from Anna?
Yeah, that's a good question. I mean, when can we get out on the market with the combination of oxygen and water barrier and so on? And I think that's it's possible to do it quickly. But the question is, what do we aim? And that's the problem with this sort of plastic replacement thing. Are we aiming to fix the littering in the ocean, or are we aiming to make a perfect circular society, or are we aiming to get rid of the petroleum oil? There are different approaches here. So I think, I mean, and then there's also always a pricing thing as well. How much are the customer ready to pay for something? So those are the let's say 4 parameters that is a bit challenging to handle. So the dream is always, I mean, to say replace aluminum, polyethylene, polyester, laminates are different kinds. That would be great to do it. The shelf life won't be the same, of course. The price won't be the same. etc., etc. So there is a price to pay for someone. If someone is ready to pay the price, I think we could go quite quickly.
May I add a comment here too?
Absolutely.
I also think that Mikael and I have really shown that there are two perspectives and two timelines here. And one is the one that is very close to market, which Mikael showed some example that you actually have products on the market. It's a very much shorter where you look at current solution, while what we're looking at in the research is really to see what kind of solutions that we can develop. And that is a totally different timeline. So what Mikael is talking about is a timeline between 6 months and a year maybe, whereas what I'm talking about is 3, 5, or maybe even 10 years in some cases.
Okay, so we actually have some other questions addressing this. I think that the questions are reflecting on the fact that there's a big need for getting something out there on the market as fast as possible when it comes to bio-based barriers. Another question here from Paula Pinto is, how do you see xylane isolation at industrial scale?
Well, I mean, it's done at an industrial scale, and there are various companies doing that. You even also have a startup company from KTH, which is called EcoHelix, that are doing this, and they're also processing the hemicellulose afterwards. So, I mean, and then there's also other resources of wood. You actually have in agriculture products that you can use different side streams, and I believe that is what's done with Scalax solutions, hemicellulose barrier, that they're using farm resources or side streams there. So I mean that is done in industrial scale today, and so it's something that can be done, but regarding the economics, I got to pass that question actually.
Well, actually, I think that when it comes to new technical platforms like this one, it's always you have to have the courage to be able to put it out on the market and then look at the economic benefits of it as well. So it's very complicated. There's also another area of interest here, and that's the recycling. So Sampo Immonen has actually asked if efficient reuse/recycling is possible with paper, board, with bio-based barriers that are multiple, when you have multiple barrier properties, like for water, grease, and oxygen.
Well, if we look at today, well, what's done is that you're actually separating the board from the multi-laminate, and you're burning the laminate for energy. So that is one way of doing it. But I think this is a very complicated question that it seems very simple. If we look at something that is dispersion coded, we might actually be able to recycle it with the fibers directly. It might form some stickies and other unwanted substances, but in the long run, I think that is definitely a way we need to go. However, I think that we also need to address this question better in research. There is definitely research needed here.
And that also, I suppose you almost answered Hakola's question, where it says that can the different barriers be organized in layers so that the topmost layer are not disintegrated when exposed to contact with materials, for which the barriers are below the top layer. That's also, I suppose, it doesn't have to do with the recycling, but it has to do with how you set up the layers.
I can answer that question. Yes, you can. I mean, that's what we normally do with when you have most of these commonly used oxygen barrier plastics, and they are quite sensitive to humidity and so on. So that's normally protected then by a polyethylene layer or something like that. That also provides with the sealing properties and the water barriers and so on. So that's exactly what you do. Just to go back a bit on this recycling of paperboard and so on. Yes, you separate the plastics from the board or the barrier from the board, and that normally the plastics are recycled as well. Not in all sites, but that's absolutely possible to do up to a certain level. I mean, if you add too much of new biodegradables or other materials that are difficult to reprocess, then it's going to be some difficulties, and you cannot really separate the layers perfectly. There are some methods on solution disintegration of a multi-layer coating, for instance. That's still under, I would say, under development. So the common three methods are not really aiming to separate any layers that commonly are very thin. But if you can, you do put it into the polyethylene stream, which is the common way to also recycle the, milk cartons and so on.
Great, thank you very much. I think we will stop there. There are quite a few other interesting questions in the chat, but we will address that in the mail. So you will have to answer that after the seminar. I hope that's okay, Peter and Michael. And we will send that in the mail that we will send out to all of you that have been participating in this breakfast seminar, because we want to finish on time, and we are very eager to get a little bit of input from you who attended with a Mentometer. So I would like to urge you all to bring out your phones, your smartphones, and go into menti.com and enter the code that you see on the top of this slide, 386994.5. If you could do that, we would appreciate it very much. We just have a couple of questions. And if we go to the first question, I see the questions are still coming in here, and we will be sure to answer all your questions. So the first question on the Mentometer is, please give us your rating on the presentations today. We'd like to get some input from you, both on the separate presentations, but also on the overall impression of the seminar. And we appreciate that very much, to be able to see what we will do for the next seminars. We have about a little bit more than 100 participants still on the seminar, so we will see how many of you can actually get onto the smartphone. Can we move to the next question maybe, and you can still vote on the first one. We'd also like to know how you got the invitation for this seminar. This is valuable information for us, for how to. And the last question, thank you, Elena, is actually, please give us some feedback on ideas for future topics. And you can also actually give us some feedback on if there's something that you would like us to improve on. And Helena and I are, as we said, we have one seminar left for 2020, and then we will regroup and see what the themes will be for next year. So we are really anxious to get all the inputs we can get from you on the interesting topics. Right. It's very good. With that, I think we actually are pretty satisfied with your responses. And I thank you all so much for attending and also for posing all the questions. And we will get back to you all with the answers of the questions that did not get the chance to get answered here. So with that, Peter, Mikael, and Helena, can you show your face too? I don't know whether she's quick enough. Yes, there you are. So from the four of us to all of you, thank you very much for today and hope to see you in future breakfast seminars.
Thank you.
Thank you.
Thank you.
Thank you. Very nice.
Thanks.